In this section, I'm going to derive the expression for angular magnification for a simple magnifying glass in two situations. The first, for when you're looking through a magnifying glass and you can see the object at the near point. And the second situation will be where you see the object at infinity. First, we need to define the idea of magnification. Okay, magnification is a simple ratio. If you can imagine looking at an object, I'm going to scroll a tree on here. Okay, so there's our tree. Imagine yourself looking through a magnifying glass and seeing a big tree, okay, compared to if you're looking at the tree with just your eye. The angle, basically the whole range of the object, the light from the object that comes into your eye, if you can imagine the angle that the top and the bottom makes with your eye, that would be the angle subtended, okay? So the magnification is simply a ratio. What is the angle subtended at the eye by the image over the angle subtended by the eye at the eye by the object? Very straightforward. And it gives you an idea of how much bigger the object will be through the magnifying glass. Okay, in order to derive the relationship for a magnifying glass for an object at near point D, we're going to use the following relationships. The first one is the relationship for magnification. Magnification equals angle of the image over angle of the object. The second relationship we're going to use is the thin lens formula, which is 1 over f equals 1 over u plus 1 over v. And the third, which is more of a mathematical simplification, if the angle is small enough, tan of the angle equals the angle. Okay, now let's begin with our derivation. Magnification, as we say up here, is equal to the angle of the image, or the angle subtended by the image over the angle subtended by the object. Now, we're considering here this point D, this distance D, which is the distance to the near point. Remember, the near point is the closest possible distance that an object can be for you to be able to focus on it. Now, we're going to consider the angle of the object. Imagine if you did not have that lens at all, and it was just your eye looking, okay? If you put the object HO, okay, at the near point, a distance D, okay, then you would have your angle. Okay, that would be the angle subtended to the object. And that angle would be equal to H0 over D. Okay, so we would have angle of the object would be equal to H0 over D. When we do use a magnifying glass, we are assuming, or we're basically doing this exercise for a virtual image at the near point. Now, when that's the case, the angle here can be worked out by dividing the height of the image by the distance D. So what we have is, in this case, the angle of the image is equal to H1 over D. Now we can substitute both of these relationships in. Whoops, that one would go in there, and this one would go in here. And we would end up with magnification equals H1 over D divided by H0 over D. And that would leave us simplifying, getting rid of the d's and ending up with magnification is equal to the ratios of the heights. Now, if you look at the formula that we need to end up with, we need to try and make magnification, express it in terms of the focus. So we're going to go back to our thin lens formula, this one here, and we're going to try and use that. And there's a couple of steps. The thin lens formula, 1 over f equals 1 over u plus 1 over v. And we're going to multiply each term by v. Okay, 1. So that will give us v over f equals v over u plus v over v. Now we can already simplify because this would give us 1. And now we need to look at our diagram again. If we remember, the distance v corresponds to the distance between the virtual image, or any image, sorry, the image and the lens axis. Okay, and in this case, it's equal to d, the near point distance. So v equals d. So we can substitute that in here as well. So the v that we have here, we can replace with d. And now let's have a look at this ratio, v over u. If we go back to the original diagram, we can see that there are two triangles, or two similar triangles. We have h1 over capital D, which give us this angle here, okay? But we also have a similar triangle, h0 over u, which gives us the same angle. So using this idea, we can say that h0 over u equals h1 over v. Okay, and we rearrange this, we can see that h1 over h, it's actually h of the image, sorry, over height of the object equals v over u. Now, why is this helpful? Well, we can see from here that the height of the image over the height of the object is equal to the magnification. And it's also equal to v over u, which is here. So you can substitute magnification for this term here. So now that gives us an expression, d, the distance to the near point over the focal point, equals magnification plus 1, which is where we were supposed to get in the first place. Okay, and that is a formula that you can see up here, oops, gone too far, for an image at the near point. Okay, so we're going to try this again, but this time for a simple magnifying glass with an image at infinity. And we should end up with this relationship. So let's start with, again, the first situation, which is what happens when you get rid of that lens and you consider the angle subtended to the object without the lens. And this object placed at the near point would give us an angle equal to the height of the object over the distance from the center of or the supposed center of the lens to the near point. So that's without the lens. Now with the lens, the angle that the image is projected to is the height of the object. Okay, you can see it here, this height. In order to make this angle here, it'll be the height of the object divided by the focal length this time. So you would have, height of the object over the focal length. Okay, so we end up with magnification is the angle of the image over the angle of the object, which is equal to the height over the distance to the near point and the height of the object over the focal length. So we can simplify that and it will give us m equals df, which is what we have here.